Good afternoon, everyone. Thank you very much for being here. I'm Jeremy Picot-Clement, technology specialist at EPIC, and I'm really pleased to moderate this online session on mining and geology, so photonics for this application. A few words about EPIC before to start. So EPIC is the largest industrial network in the world in the field of photonics. We have today more than 800 members covering all the value chain of the photonics industry, from the component manufacturer, the design and prototyping company, to the end users and system integrator. We also cover all photonics application, which is quite wide, from space and defense to biomedical and quantum, including AR, VR, agriculture, photonic integrated circuits, and laser technologies. Our aim is to create a sustainable open photonics industry, and how we do this. We offer a large panel of services to our members, to EPIC members. We offer technology support, market and technology report access, networking event, networking opportunities for you as a member, access to market, USA, Asian, maintenance support, HR support, and investment support. Here is the team, the EPIC team. So we are all passionate by photonics. I'm personally a part of the technology team with my colleague Antonio Castello and Ivan Nikitsky. But then we have a marketing team and also a logistic team. And what we do in terms of events, so we organize physical events, but also online meeting, at the one of today. So about physical meeting, as I told you, we cover all the photonics industry or the photonics application. So in few days, we'll organize something on photonics integrated circuits at Legiantech in Switzerland. We'll be at the W3 fair in Wetzlar, Germany. We'll organize also the annual general meeting in Barcelona, Spain. So we'll be at OFC in USA. And in April, we will organize a meeting at Thales on disruptive optics. We'll be also at More Photonics beginning of June, talking about AR and MR photonics for these industries. And then about online meetings. So here it's wider since we cover also some marketing topics. So we will have an EPIC market report on metamaterials and metasurfaces by thematis. An OTM, so online technology meeting on laser processes for automotive, an online marketing meeting also in April, then a members new product release, an online technology meeting on new development for microscopy and bioimaging, and an online technology meeting on photonics computers. As I told you at the beginning, we cover all the value chain or the supply chain of this industry. So we have some end users, system integrators, equipment manufacturers, component and modules companies, service providers, software and design companies, research and development center, of course, metrology and testing, distribution. So all these companies registered for this event, and will have access to this on the webpage of this event afterward, after the meeting. And also a few words about the agenda of today's event. So we'll have 6 presentations, 6 talks. We'll start with Marco Celesti from ESA. You will talk about Copernicus hyperspectral imaging mission from the environment. We'll continue with Justus Constantin Hildebrand from HiSpecs. You will talk, Justus, about hyperspectral imaging in mining environment. Then Seiya Matsumoto from Hoya, high quality, high refractive index optical glass for aerial surveys. Then we'll continue with Olof van Hofsten from Eclipse Optics. Olof, you will present several of your projects related to optics and also focus on imaging and LIDARs. And also we'll continue with Evgeny Gunovich from Technology Innovation Institute. You will talk about millimeter waves for drilling in oil and gas geothermal industries. And we'll end this meeting with Vincent Menoret from Exail. And Vincent, you will talk about quantum sensors for geophysics. So thank you very much again for your participation. Feel free to send me an email if you want to be introduced afterward to one of the speakers, one of the participants of today's event. And feel free also, if you have any question, we'll keep some time after each presentation to question and answer. So if you have any question, you can raise your hand through Zoom, in the Zoom chat. So thanks again, and now we can start with Marco Celesti from ESA. You are Earth Surface Hyper and Multispectral Optical Scientist. And Marco, please, you can share your screen and start your presentation. The floor is yours.
Thank you very much, Jeremy. I hope you can still hear me well. And, and in a moment, see my screen. I'm indeed an Earth observation scientist. In particular, I'm the mission scientist of CHIME and FLEX, two future Earth observation missions. And my presentation should be coming in presentation mode.
Perfect.
Can you just confirm? Okay.
Yes.
Okay, very good. So I apologize in advance for going very fast through some slides, but I will be happy to share the slide deck with you all afterwards. So very quickly, CHIME is today I'm focusing on CHIME, the Copernicus Hyperspectral Imaging Mission for the Environment. It's a mission which is part of the Copernicus program, for which ESA is basically the implementation actor and for the European Commission, and CHIME in particular within the Copernicus ecosystem provides data, provides spaceborne measurements and subsequent products to stimulate the uptake from end users. The Copernicus services, for sure, our core, say, operational producers of data for the European Commission, but also much larger number of scientific and operational users who feed and are part of what we call the downstream economy of which is enabled by the Copernicus data, free and open for all sorts of use, as you know from the last years, most likely. CHIME is part of the 6 Sentinel expansion missions that you have here. In particular, it's focused on some, let's say, critical application domains and the exploration and exploitation of raw materials is one of them. So that's why we are talking about CHIME today. In principle, the CHIME mission objective is to provide routine hyperspectral measurements at global scale over all land and coastal areas, and it's targeted to support, in particular, European and global policies for the monitoring and management of natural resources and food security. So there are 2 primary application domains for which the mission has been designed, which is agriculture on one end, so vegetation, crops, and soil monitoring, and the other one is raw materials, so basically minerals. That's cool. There are a number of secondary applications which will be enabled by the availability of CHIME data, but these are not what, let's say, we're not driving the mission design. So what is the mission design? In principle, in the key specifications are that CHIME will be a carpet mapping mission, so a la Sentinel-2, so to speak, not tasking, but carpet mapping of all land and coastal areas, quasi-nadir observation, I mean the nadir pointing with a relatively small SWAT, in field of view, up to 84 degrees sun zenith angle, covering the full spectral range linear to sphere 400 to 2500 with a spectral sampling of 8.4 and a full width of maximum, so spectral resolution of about 10 nanometers. All this at 30 meters spatial resolution, which with 2 satellites, which is the final constellation, brings basically an 11 days geometric revisit, with, of course, a slightly better coverage time at latitudes higher than the equator, basically, due to partial orbit overlap. We ensure that this is done with a very high radiometric accuracy, high SNR, and a very low spectral and spatial misregistration in order to enable basically full spectrum retrievals as much as possible. So the user data products, which will be produced routinely, are top of atmosphere radiance and reflectances, and bottom of atmosphere atmospherically corrected surface reflectance. We are planning to, we're building our processor in order to be able to generate these layers, the surface reflectance layers, both in the original sensor geometry to avoid any spatial mixing, and in auto-rectified geometry, basically, with associated uncertainties. And just going very fast, these are the prototype products that we are currently developing in order to demonstrate some of the potential of the mission. This is not meant to be operational products. It's not in the mandate of ESA at the moment to provide any operational product beyond surface reflectance. Okay, but in order to prototype, to show what we can do, we are developing some retrievals, and there is also something related to geology application and minerals. However, I must admit that there is much more to do on that, based on heritage and on let's say future development. And I'll show you some examples based on missions which are already flying, imaging spectrometers which are already flying. Here, an example from NMAP, from DLR, launched in 22, and it's just an example of a site in Chile, where basically they managed to map the alteration minerals, and I think this is white mica specifically, and the position of the minimum of the absorption of white mica in order to identify aluminum rich and aluminum poor areas. Basically, of course, we are limited to the very surface. Remote sensing and optical remote sensing cannot solve each and every problem, but whenever there is exposed rocks, basically, and soil for other applications, we can definitely do something. Here, just another example from our colleagues at JPL, with which we are constantly working of the applications of the tetracorder algorithm to an emit image. Emit is another imaging spectrometer on the ISS, and through the combination of a large number of observations from it, actually, our colleagues at JPL have been able to prototype and to demonstrate, let's say, the first regional maps from an imaging spectrometer with real data, and you can find much more details in the publications and online from our colleagues. But very short, sorry, I didn't check what time I started, but I will just go through quickly through the other slides. In principle, the space segment is going very well for Chime. So the contract, actually, we're now in the CDR of the entire system. So the critical design review, it means that after in a few months, basically the full design of the entire satellite and instrument will be completely fixed. There is not much wiggle room, to be honest, already now, but this is because we are performing very well vis-a-vis the requirements so far. So we are actually on a very good track. It's just for your information, let's say, a view of how the instrument is assembled, and the three spectrometers, which basically build up the unique 130 kilometers watt, unique, of course, for an imaging spectrometer so far. And this gives us basically the capacity of doing the carpet mapping and every 11 days with 2 satellites. This is just for fun. If you want, you can have a look at one of our latest tests, where a model of the full instrument has been tested for all sorts of vibrations. I want to highlight that we have in order to prepare for Chime, we have developed a full end-to-end simulator where we generate scenes, or synthetic scenes, from in the performance, in the scene generator module, and then we replicate, we propagate the top of atmosphere, we replicate the observation, we can test basically our level 1 processing, level 2 processing, and then check the performance versus the inputs of all this process. And one of the inputs of all this process can also be campaign data, which I want to point you to because they are available. We have had several campaigns, particularly a large one in 2021, where a number of sites have been imaged with an airborne sensor, but also by Prisma, another imaging spectrometer from the Italian Space Agency. This data set is available. If you're interested, just let me know. And we have incredible exchange with our international partners in order to build basically a common ground for global imaging spectroscopy. This is a golden era for us. With the community has been waiting for these imaging spectrometers to become a reality for many decades. And recently we gathered this community at ESTEC in November for a third of a series of international workshop on international cooperation of spaceport imaging spectroscopy. I leave you these links if you want any further information on CHIME, and thank you very much for your attention and your time today.
Thank you very much, Marco, for this nice overview of the CHIME project. Any question for Marco? You can raise your hand through Zoom. You have the button at the bottom of the screen. And if you have any question, you can click on it. I will give you the floor. Maybe one question from my side, Marco. I was wondering how do you ensure the high radiometric accuracy in areas with with a frequent cloud cover?
Well, we have so for us, clouds are of as much as a problem as for any other optical missions, and there are two elements. One is the masking of them, and this we do in a two-step. First, on board we have an onboard processor which identifies thick clouds, and we selectively compress those pixels much more than the, let's say, relevant pixels, so what we consider cloud-free on board. There's a very conservative process in order to avoid loss of relevant pixels, but this saves us a bit of bandwidth and to say maximize the quality of the other acquisitions. I'm not sure I catch completely your question, because I mean, apart from the masking that then is done on ground on this, and we have are you referring to stray light impact due to clouds, or
No, it
be
was
more precise, maybe? Sorry.
Yeah, it was mainly about the area with cloud covering. How do you ensure the accuracy of the measurement from a high perspectral cameras? Because you are not, you pass by this kind of areas every 11 days or something like this, every 10 days. So how do you ensure that this area is well covered? If sometimes you have
Well, unfortunately, if we don't have visibility, I mean, there's not much you can do. Huh?
Yeah.
I mean, if it's cloudy, it's cloudy. It's repeatedly cloudy. Unfortunately, there's not much you can do. And the thing is, when it's sufficiently thin clouds, so then in our atmospheric correction pipeline, there is let's say you correct as much as possible. We don't have the exact numbers now, because the atmospheric correction is currently in development. We will receive the first prototype towards the end of this year. But basically, we are very consistent with what NMAP is doing, because our atmospheric correction is developed by DLR's Prime, based on the heritage from NMAP, and yeah. Unfortunately, I mean, we can't beat the atmosphere. So
And you
so when it's cloud.
You mentioned international collaboration. So do you share share all the data you collect? How does it work exactly?
Yeah, sorry, maybe I flew very fast here. So Chime will be part of the Copernicus, the Sentinels, basically. Yeah. So the license which today you have for Sentinel 1, 2, 3, so the Copernicus license fully open for any use, also commercial use, is not expected to change. So unless the Commission decides to change the Copernicus license, Chime will follow the Sentinels, the current Sentinels, and be free and open for any user for commercial and scientific exploitation.
Mm.
Today, of course, when it comes to our let's say simulated data or the information that are industry related in terms of characterization, calibration, this is more tricky. We have to do it ad hoc. But if there is sufficient reason, we can think to share some of our simulated data set, for example. If someone is interested to start prototyping, applications in view of Chime. So we have a recent program which is called Sentinel User Preparation at ESA. The first call was released last year, and it's indeed to maximize the preparation to exploit this data. So there will be more calls in this SUP, Center User Preparation Program, starting already this year. So stay tuned.
Perfect. Thank you, Marco. And just one question regarding your hyperspectral systems, imaging systems. Did you develop everything internally at ESA Tech, or did you work with some
No,
companies?
I can, sorry, maybe do you still see my screen
No,
or stop?
you have to share again.
Okay, sorry, because I really went fast, but the consortium is large and it's led by Thales Alenia Space
Okay.
France, who's the prime for the entire satellite. OHB in Germany is the prime for the instrument, and then there is a number of companies. Other major players are Leonardo, still involved in the instrument and in the end-to-end calibration of the instrument, and then Amos in Belgium for the 3 spectrometers, because the instrument is made of a single telescope, but then there are 3 spectrometers which are staggered in the instrument and basically built up the SWOT.
Okay, so it's a huge
Build up the
consortium.
SWOT.
Yeah. Okay.
Yeah.
Okay. For 44, you have 44 partners in this consortium.
Yeah, it's 17 countries, and
Okay.
I mean this slide is from a couple of years ago, so it may be that we have some more who joined more recently, but yeah, it's a large consortium.
Okay.
And also you see with a number of small medium enterprises, it's 13% of the entire budget, which is allocated to SMEs. So it's not just large space integrators who are involved, and there are also some let's say not purely commercial players who support that. And then this is only for the space segment. Then there is all the ground segment, which is in preparation with level 1 and level 2 operational processors in development, and the end-to-end consortium is another big chunk of it. But of course, in terms of numbers, let's say the space segment, it's the vast majority of the cake, and this is represented here.
Okay. Okay, Marco, thank you very much. So do you have a question for Marco?
One information that I did not add to this slide is that although we don't have a launch date, we have a readiness for launch date, which is end of 28, beginning of 29 at this moment. And so pending the availability of a launcher, the space segment will be ready for this date.
Thank you. Perfect. Thank you very much, Marco, for your nice overview of this project. So thanks. And now we can move with our next speaker, Justus Constantin Hildebrand. So Justus, you work as a hyperspectral application engineer at iSpecs. And please, you can start your presentation. The floor is yours. Justus?
Yes, let me try to
Okay.
resume. You should see my screen and you should see a presentation now.
Yes, perfect.
Perfect. Okay, then I will start. Thank you very much for hosting me here today. The title of my talk is Hyperspectral Imaging and Mining Environments. As I said, my name is Konstantin Hildebrand. I work as a hyperspectral applications engineer in the applications department at HiSpecs by NEO. NEO, or Norsk Elektro-Optikk, was founded in 1985 as a spin-off from the Norwegian Defense Research Establishment. It is owned by a foundation established by the founder, Tycho Jäger. Its vision is to support arts and applied physics projects in the field of electro-optics with the potential for higher impacts. We, so NEO, are an R&D-based company collaborating on a variety of internal, national, as well as EU projects. Currently, we are around 70 persons with our headquarters in Oslo, but we also have commercial offices in the US and Germany, as well as a daughter company in Sweden. HiSpecs is the HSI division at NEO. We have a commercial line of HSI products commercialized under the HiSpecs brand, serving from high-end research to industrial customers. And the markets are ranging from laboratory setups via UAV applications to space applications. We have a wide variety of cameras, which are specialized for each of the shown applications here. We do have a long-lasting relationships to mining projects and a lot of collaborations on geological exploration activities with international research institutions, for example. This is the basis for our expertise and competence for mining applications, especially with a focus on spectroscopy. In the following slides, I will show 5 different applications of HSI in mining that we did so far and that we are very interested in. I'm going to explain, or I'm not going to explain the basics of spectroscopy here because the short time frame doesn't allow for it, and I think many of the people listening have some background or at least a basic understanding of it. Let's talk about HSI laboratory measurements as a complementary method for quality control. HSI can give you an additional layer of information compared to classical methods like XRD or XRF. It can also work in real time, and it's giving you an immediate access to information, so it is very quick. We think that it's not a method to replace XRD or XRF measurements, but it's rather an extension, as you can combine it with them as well in your modeling process. On the small illustration here, you see a small stage it's a small setup for laboratory scans. You can scale this basically to any size if you want to. So you can have a small stage, large stage. It can be mobile, it can be stationary. There are basically no limits. This is an example of mineral identification with such a system. It's a mineral identification in mixed samples. The models were based on the pure samples and then applied to the scans you can see here. You can apply a variety of models to your samples, of course, whatever you want to. You can predict classes, you can predict quantities as well. And overall, it can help a lot to reduce the lab analysis time compared to the traditional methods that you usually see in the mining environment. Let's talk about truckload scanning. You can already, or you could already allocate trucks inside the mine based on the material identification of the truckload. By scanning the top layer of the bulk, you can estimate the bulk material and send the trucks to different crushers, for example. You can also combine this information with the conveyor scans after the truck has dumped the material into the crusher. This is how the real world example looks like. So we went to a mine, we went to a crusher, we mounted one of our cameras, a sphere camera, on top of the crusher. So the sample in this case, the truckload, is moved under the camera by the truck driving. And the classification results that you can see here as an example are based on USGS MICA classification algorithm. And it already shows you a clear difference of quality based on the mineral composition between the different trucks. Moving on to conveyor belt scanning. Conveyor belt scanning gives us the opportunity to monitor much more surface than on the back of the truck, for example. This is an example from the conveyor belt that is mounted or installed after the crusher I just showed. And we can have a continuous assessment of quality and volume as we can classify and quantify the material on the belt. The volume estimation can be done, for example, with a laser profiler. All of this can also run in real time, so it is very fast. You get the information directly from the scans, and the data can either be stored for a long-term historical database if you want to, or it can only be temporarily stored for decision-making on how to manage the material that is on the belt. Here again is the applications example. We installed our camera and light source over a conveyor. This is an experimental setup. So the setup that is installed at a site is usually then in a protective housing, and it is enclosed and protected from dust and has its own ventilation system. In this data example here, we scanned 150 meters of that conveyor. On the bottom of the slide, you can see that. The resolution is 3 millimeters per pixel, and that ended up in a scan that's roughly 9 gigs large. Moving on to my favorite topics, that's drill core scanning. I think it's a great application. And mining companies usually drill boreholes already and analyze the core that they're getting out of it. But scanning them with HSI and correlating a mineral identification to the depth of the core is a huge opportunity to improve the current methods. On the right-hand side, you can see a high-resolution core scanner by us. It is able to scan 1 or 2 cores at the same time in a very high resolution. And you can see the results of that scan on the left-hand side, visualized in RGB and also visualized in different classification algorithms. Talking a bit more about drill core scanning products. We have an upcoming delivery, a large system going to Alaska. It has a mid and long wave infrared sensors as well. And it also has the new high-specs generic core scanner head. And that is a unit consisting of 2 cameras and a laser profiler. We have a veneer and sphere, so we have a combined range from 400 to 2,500 nanometers. And these are going to be co-registered very precisely using the laser profiler. This setup, not only that large setup, but the core scanner head that we are going to supply to our integrators or customers directly allows for the integration of other sensors as well. And you can either get this as a module that you can integrate yourself or as a fixed solution. Let's talk about the last example of HSI in mining. It is remote sensing, aka having the camera on a satellite or drone mounted. I will focus on the drone application here a bit more. This allows for a bunch of applications, as you can see, especially important regarding the project I'm going to show you, tailings monitoring and open pit mapping. The M4 mining project. As already mentioned, we are an R&D-based company, so we are collaborating with EU-funded projects. This is one of them. The abbreviation stands for multi-scale, multi-sensor mapping and dynamic monitoring for a sustainable extraction and safe closure in mining environments. It aims to improve the characterization of material during the extraction and remining. And the goal is to map and monitor active, but also inactive mine sites using UAV and satellite-borne sensors. This all will be achieved in real time. This means we have a real-time reflections retrieval without any white references in the mine, as well as a mineral classification, and everything will be visualized in 3D. This short video shows you the software size of the project outcome. The project will end in 2025, and both hardware and software will be available second half of the year. So what you can see here is the live visualization of the drone and camera position. We have a large 3D surface model, which was generated in the first flight line. And now for the second flight line, we can see the RGB and classification results that the camera is measuring in real time. And you can toggle from the RGB view to, in this case, the USGS Mica classification algorithm. And this is one of the main outcomes of this project. If you're interested in seeing this demonstrated live in September in Germany, we have a demonstrator there. Feel free to contact me or contact us. Looking at the time here, I'm moving on to the last slide. What can we offer? What do we need? We offer finalized products. We offer customized and individual solutions. We have the hardware and we have the software. We do a lot of research and development, as this is the focus of the company, and we are and we can be partner in private and public projects. We have a solid network of suppliers, but we are always interested in hearing out what other companies can offer to us, mostly in regards to new detectors, high SNR detectors across the Veneer and sphere range, custom lenses, mirrors and gratings, high precision mechanics. And we also use calibration equipment that is not from us, such as spectral lamps, lasers, integrating spheres, and white reference panels. Yeah, let me conclude with that. And please, if you have questions, please ask them.
Thank you, Justus. Thank you very much for your nice presentation. So any question for Justus? Yes, Robert Little from Foreign Affairs IOF. Please, Robert.
Hi, thank you for the talk. I have two questions, I saw that you use the sphere band and a halogen lamp for illumination of your of the material. How many channels do you use for the sphere application to calibrate for a certain material, like the limestone or so? How many channels you need in the sphere?
Yeah.
And how specific are your filters you are using?
Let me start with the first question. So depending on the camera we are using, we have a different amount of bands available. If we are talking about the classic series, so our cameras that are for the lab but can also be used somewhere else, on a conveyor, for example, we have the highest amount of bands. Also, depending on the spatial resolution, we have different amounts of bands. And we usually starting something with the highest amount of bands that we have available. And if someone decides that they want to have an industry line of cameras which have less bands, which is faster, etc., we are trying to test if we can see the same results with the different camera as well. So depending on the camera we are using, we are talking about 100 bands to 300-400 bands. And I can't give you a definite answer to the minerals you were asking to, but I can look into that and give you that information. For those minerals active in the sphere region, it is not only important how many bands you have in total, but how many bands and how close they are together in that specific region where we have very narrow features. And for the second question, I didn't quite understand what you mean by the filters. So it would be great if you could,
Yeah, so it means rather how specific is if you have a line or for limestone, for example, And then for clay, just two, I know in English, but how specific can you say, okay, you go to this mine because you expect a material and you see it's there or it's not there, and there are contamination of whatever. How specific is your filter set you are using when you fly with a drone over the
Okay,
scenery?
okay. I think I understand it. We don't have any filters. This is a push broom system, so we are acquiring raw data, then we convert
Okay.
the radiance and pure reflectance.
So this is no snapshot. It's push
No,
broom. Okay.
it's a push broom sensor.
Okay. Okay.
Thanks.
Thanks. And this is maybe only one question. How compact is this application you have, the camera you have on the drone, because it needs a certain mass?
Yes. So the classic cameras are larger, more heavy, and we combined both the veneer and sphere into it's called the Mjolnir. It's our drone-based camera. It weighs around 6.5 kilos, and if you want to add a LiDAR to it, it's just 1 kilo more. So we are talking about 7.5 kilos max for the system on a drone. We are operating this either on a drone that barely touches the 25 kilo mark, or on a heavy lifter drone that is 36 kilos, all depending on the regulations, on the pilot who's doing the job, and also on the budget and flight time you want to accommodate for your mission.
Thanks a lot.
Thank you, Robert. Any other question? So
I've seen the question in the chat. I don't know if I should.
yeah, sure. Please, Justus. Maybe the person who asks the question can take the voice, huh? If it's okay. We have a question also from Radha Krishnan from Crispy Project. Radha, can you ask your question by yourself?
Hi, thank you. Thanks for a nice presentation. This is regarding the mining contract, because normally the mining will be auctioned, the highest bidder will get the mining. And what happens is those people who are allowed the contract, they tend to take multiple times higher than what has been allowed. So my question is it possible to just give the evaluation and check how much was extracted from the mining, just to give a volumetric data, or is it possible with this technology? Thank you.
Thanks for the question. That should be possible, but it depends on a few things. You can't really fly with a drone and then estimate how much material was extracted. I think this will be very inaccurate. You can put the system on top of a conveyor belt and then have a volume estimation about everything that goes on that conveyor. But if you have material that is not going via that conveyor, you can't monitor it.
Okay, thank you.
Thank you, Radha. Last question. And if not, let's thank our speaker again. So thank you, Justus. Thank you very much for this presentation. And let's move on with our next speaker, Seiya Matsumoto. So Seiya, you are a sales engineer at Oya, and you will talk about high quality, high refractive index optical glass for IRL service. So please, Seiya, the floor is yours. You are muted, huh?
Yeah. Can you hear me?
Yes, perfect.
Okay.
Thank you.
Thank you very much, Jeremy, for your introduction. So I think you can already see my screen.
Perfect.
Great. Okay. So thank you again, guys, for this opportunity. My name is Seiya Matsumoto, and I'm a sales manager at Hoya Optics Europe. Today, I would like to present high quality, high refractive index optical glass for aerial surveys. So here are the key topics I will cover today. Brief introduction to Hoya, who is Hoya, what's Hoya doing, and key features in developing an aerial survey camera. Number 3, benefits of using high refractive index class. Number 4, challenges and Hoya's solutions. Number 5, advantages of using Hoya's class. And the last one is EPIC's typical questions, what we can do for you and what you can do for us. So Hoya is a Japanese group company headquartered in Shinjuku, Tokyo. And we have approximately 36,000 employees worldwide and generated about 5.08 billion euros in revenue in financial year 2024. And Hoya operates in 4 product segments, and we belong to the smallest one, this imaging segment. Actually, I'd like to explain our product portfolio in more detail, but today I have a limited time slot, so I will skip it and then jump straight into the aerial survey application. So when developing an aerial survey camera, several key features must be considered. And number 1, high-resolution sensor. Without a high-resolution sensor, precise images cannot be captured. Number 2, wide dynamic range as well as high dynamic range. Due to the high contrast between bright and shaded areas and the influence of the sunlight, a sensor with both a wide and high dynamic range is necessary. Number 3, precise location information. A high-quality GPS system is essential for accurate positioning. Number 4, multispectral and hyperspectral compatibility. Not only is broadband imaging, but also various wavelengths such as UV and NIR are required for multiple applications. Number 5, high precision lens and optical system. As a glass supplier, this is where Hoya can contribute. A high performance lens with minimal distortion and uniform image quality is crucial. In aerial surveying, correcting aberrations to maintain sharp images even at the edges is particularly important. So here are some key benefits of using high refractive index glass. Number 1, compact and lightweight lens design. Reducing the total space and weight makes mounting on aircraft and drones easier. Number 2, reduce the distortion. This improves image accuracy and enhances the precision of survey data. Number 3, high resolution and high contrast imaging. Sharper images lead to better survey accuracy. Number 4, uniform image quality across the entire field. Consistent resolutions and brightness are maintained across the entire field, even in wide area imaging. Number 5, enables bright lens design, means low F number. This allows for shorter exposure times, reducing motion blur in images. Number 6, improves the chromatic aberration correction. By using different upper numbers, it means different dispersion glass types, combinations, RGB data capture becomes more precise, such as, for example, TFT55W and FCD100. So one of the main challenges of high refractive index glass is low transmittance and UV and blue range. And appearance is yellowish due to the metal oxides, such as tungsten or titanium. You can see this picture and difference between our standard glass type TFT55 and our improved glass material TFT55W. The left-hand side seems very yellowish, and the right-hand side is more transparent. So, where the solution is to overcome these images we developed an advanced material which significantly improves transmittance particularly in UV to blue light range. So this table shows the difference between the internal transmittance between several glass materials. As a result, image captures with lenses made from W3 glass have better color accuracy and higher overall brightness. This table shows an excerpt from Hoyer's glass list featuring high refractive index glass. We have a strong presence in the market, especially with glass offering refractive index higher than 2.0, which are listed in this table in red. If you are interested in more about our glass types, then you can find details on our website. So here's some advantages to use Hoyer's glass. Number one, enhanced chromatic aberration correction. Hoyer's high and low refractive index glass offer various combinations to improve chromatic aberration correction. Number two, optimized transmittance with W3 glass. Improves UV and blue light transmission, overcoming the typical yellowish tint of high refractive index glass. Number three, and cost-effective molded aspherical lenses. Provides high precision and stable quality lenses at a competitive price, even for the high volume demands. Number four, in-house glass melting expertise. Our deep understanding of glass properties and processing allows us to optimize solutions for various optical applications. Number five, in-house optical and designers for consultation and custom design. Our experts can tailor lens designs to meet specific customers' requirements. So number six, environmentally friendly. All Hoyer glasses are free of hazardous chemicals and comply with laws and leach regulations. So now I come to the end, and there are typical epic questions: what we can do for you and what you can do for us. What we can do for you. Our in-house optical designers can consult on lens design based on your specifications. We provide support from the very early stages of development, and we offer attractive pricing for small quantity evaluations. And then, what you can do for us? You can involve a glass manufacturer early and development stage. And instead of specifying only one glass type, allowing more flexibility in material selection can lead to optimized solutions. We, as a glass supplier or your partner glass processing company, know the glass characteristics very well. It is not efficient to develop a good application if you specify just one type of glass and disregard other options. So, and that's all for my presentation, and thank you very much for your time and attention, and any questions are welcome.
Thank you very much, Seiya, for your presentation. Any question for Seiya, please? I was wondering, Seiya, how do you ensure that your high refractive index glass is stable in time when you use it under atmospheric condition or in harsh environment?
Wait, I can hear you answer first.
How are you sure to keep the performance of your glass during the time, when you use it under atmospheric condition in harsh environment?
Yeah, it depends on the glass application or modules. It's not necessarily exports to the nature. So there is some, let's say, protective coating on the glass surface or lens surface, or just the customer has a cover glass in front of the lens. So there are several methods to protect the lens quality.
Okay. And regarding the yellowish challenge you have, so you have no layerish at all, or you can have this kind of effect also in time.
Yes, but we cannot apply all of our glasses, but we concentrate based on the customers' requests, which are very demanded in the market. Then we concentrate to improve the color and also transmittance inside the glass.
Okay, any question for Sir? Yes, Robert, please.
Sorry, I'm again. Can you give any remarks on how you could tool your glass? How could you work with it as a bulk material? Could it be molded, precision molded, or is it available as sheet material such as wafers? Can you give a
Yes,
comment?
yes. So we can offer several shape and materials based on your requirements. So we can offer you from the block to the final shape of lens. And if you need, then we can offer also the blanks or wafer shape. So it's up to your requirement.
Okay, thanks.
Well done.
Thank you, Robert, for your question. Do not apologize if you ask question. Thank you, and thank you again, Seiya, for your presentation. Thank you very much.
Thank you.
And now welcome our next speaker, Olaf von Often from Eclipse Optics. So you are optics specialist, and we will talk about your project in this application. So the name of your presentation is See the World Differently. So please, Olaf, the floor is yours.
Thank you very much, Jeremy, and thank you for letting me speak at this nice event. Already very interesting presentations. I enjoyed it very much. So my name is Olaf, and I hope you can see my presentation now.
Yes.
So I work for Eclipse Optics, and we're a Stockholm-based engineering company, contract engineering company. We don't have any products. We don't manufacture anything in higher volumes than prototypes, but we offer our expertise in optics and photonics as a service provider. And we started about 10 years ago, so we've been working in many different projects, and surely mining and geology is a very interesting field. So I'll present the company here today and some of the projects that we've been working on, which might be relevant to this community. Okay. So what do we offer as a service can be divided up into different areas. So we can come in different stages of a project, and we can do it on site or remote. So we do a lot of these design and simulation projects. So a customer comes to us, wants to have an optical system designed or something simulated, which involves light. So we can do that. We also do limited types of testing, lab and testing, so different materials, optical tests. We also have a camera lab in our office in Malmö, in the south of Sweden, where we can do image quality evaluation of cameras. We also take on larger projects, like going from a concept to a prototype. So this involves like other partners as well, usually, since at Eclipse we only work with optics. So we, depending on what type of complexity and application we develop a prototype in, we take in different people from our network. We also have several of us working on site with customers in their optics teams. So you may already have some optics in your company, but during a shorter time, maybe you need some extra resources. And we're happy to jump in and help out during those periods. It's also nice for us because we can work with what we love in optics. So talking about different technology areas instead, I already talked a little bit about camera technology, what we do there. And when it comes to optical design and simulation, we work a lot with imaging optics, of course. So designing objectives and different measurement systems where you use optics to make images. We also do illumination optics, LED optics. So here in this sewing machine, going sort of from these small LED emitters onto a larger area where you want to have your light. Optical metrology, with this, think about spectroscopy as well, as you already saw many applications. But it can also be sort of measuring optics and these mirrors and this solar concentrator that you see in that image is used to uses optical metrology in some way to measure those surfaces. But it can also be a concentration or absorption or something. And then we have some extra long experience with LiDAR and microscopy. And I'll show you some applications of LiDAR later on in this presentation. So here's the full team in the tulip fields of the Netherlands about a year and a half ago. We had just been taking a long bike ride, so some of us are a little bit tired in this image. But it shows like how big of a group we are, and also quite diverse in age and gender. And we have a lot of PhDs. Most of us are actually PhDs in physics. So we love to work together in our projects and develop stuff together. Some key figures just to show you. Here's a crude map of Sweden. We have an office in Stockholm where I am, and one in Malmö where we have a few 5 people working. 18 people, about 3 million euro turnover, and a lot of projects since we started about 10 years ago. About over 500. And mostly working with companies in Sweden, but also around the world. So going into some interesting projects. This is one LiDAR system we developed for Murata. So Murata is actually a Japanese company, but in Finland they had this small division which made MEMS mirrors, and MEMS mirrors can be used to scan laser beams. So we worked with them to develop this demonstrator on a very limited budget, but it uses 1550 nanometer laser and this MEMS mirror and a time of flight principle. So sends out the pulse, measures the time, goes back. And we worked together with electronics, hardware, and software, so we could develop and visualize the actual point cloud that was collected by the LiDAR. So that was very nice. And this is another LiDAR system actually developed first to discover submarines, but now it's being used for bathymetry, so measuring water depth. And it was a Swedish company that was later, as now it's almost 10 years ago, but it was bought by Leica. So it uses a combination of near infrared and visible light, laser beam. So actually 1064. And the green part penetrates deeper into the water. So you can measure also the depth of the water when you're using this airborne LiDAR, but it can also measure different things on the ground as well. So with this, we designed and constructed the LiDAR and built it, aligned the systems. We've been working with them for a long time. Trimble is another type of LiDAR. They have their office here in Stockholm, and a very high precision systems. Here it's actually used. It's the picture in the background has been used to scan our office building here in Stockholm. So I'm sitting now at the top floor of that building. And here we worked on site during a longer period to develop this LiDAR. This is a different application, but I thought it was still relevant because this is from Volvo Construction Equipment. So they build these truck loaders, and we were working with them to develop a head-up display, which is a bit challenging because the windscreen is flat. So you need to have other solution than in private cars. But we built this prototype, and we managed to meet the requirements there, and now hopefully moving on to the next step. And last, I took an example of a camera development project that we had for Veoneer, which now is Magna Automotive. So both stereo and mono cameras, working with different suppliers and requirements and specifications to meet the customer's needs. Okay, so what can we do for you? These are some different applications. My first thought was from the movie Prometheus. If you have seen that movie, it's very cool drone driving in a mine. So let's build that. Or visualization or surveying, that's what we know. We know the optics, and hopefully some application. So what can you do for me or for us? Come to us with your applications and issues, and we can help you with that.
Thank you very much, Olaf. Thank you for your nice overview of what you did at Eclipse on this topic. So any question for Olaf, you can raise your hand. I was wondering, Olaf, you work, in different topics with different requirements. You mentioned, this project on airborne, for airborne systems. How do you manage to work with such different topics? Because you are not a big team, so you have to develop new expertise every time. How do you manage to do it?
I think it's a lot about being a good listener and listening to the companies to know what they or their customers what their issues are, and then when it comes down to the actual optics, it can be very similar. Usually we can use solutions that we've had for one area in a completely different one, just changing it a little bit and reusing it. So you can benefit sort of from maybe consumer electronics. You can benefit because we've already worked with some application in automotive, and then we can use that to their benefit. So it also facilitates some type of technology spreading, I would say.
Okay. And you cover, so you come from the design of the product design, optical design, until the prototyping, or you go also further in the product development?
Usually we have not continued after the prototype. So if there is, or we could work, of course, with sourcing and testing, setting up all those different types, but we don't sort of take on responsibility for the manufacturing. We leave that to the customer.
Okay. And I have just one question, coming back to the, the optical design services you propose. Do you use, because we talk a lot about AI, and do you use AI today to support you to find some innovative, optical design? How do you see this in your daily work?
Yeah, certainly a very hot topic and interesting so far. I mean, we have not been seen any real need to use AI for optical design, but we do use it for, as everyone else, like in programming and to summarize information and all of that. But just for the optical design is usually we haven't seen any real benefits yet, but we'll shortly.
Okay. So thank you again, Olof. Thank you very much for your presentation. So now we move on to our next speaker. We welcome Eugenie Gunevich from the Technology Innovation Institute. So Eugenie, you are a senior microwave researcher, and you will talk about millimeter wave for drilling in oil and gas geothermal industries. So Eugenie, you can share your screen and start your presentation.
Okay.
And maybe if you can also switch on your camera.
Yes, of course. Can you see me?
We can see your screen, yes. We can't see you. We can't see your face.
Okay. Now, I think now we will be able.
Yes.
Okay. Thank you very much, Jeremy. Good afternoon, everyone. My name is Evgeny Gurnevich. I'm from the Directed Energy Research Center from Technology Innovation Institute, Abu Dhabi. And my today's talk is devoted to one of the projects that our research center is currently working on. So the topic is millimeter waves for drilling in oil and gas and geothermal industries. So why do people drill holes in the earth? Obviously, it is required for the oil and gas industry and, for example, to access underground water sources. But there are other applications of drilling, both purely scientific and practical, like, for example, nuclear waste storage in deep holes. But let me highlight the actively developing direction of geothermal energy sources. As is well known, the temperature underground increases with increasing depth by about 25 degrees per kilometer. So the main idea is to pump cold water or another coolant like liquid CO2 from above into a deep well, where it will be heated and rise to the top in the form of steam and hot water. The rest should work in the same way as for all modern power plants. At the same time, in order to significantly increase the efficiency, it is desirable to have the highest possible water temperature, because especially at 373 Celsius and 220 bars, the normal water becomes supercritical and its heat capacity increases rapidly. That is why achieving high depths, let's say 12 kilometers and even more, for enhanced geothermal sources is very important. So what could modern technologies offer? Of course, mechanical drilling. This technology is fully mature and has all the benefits that this entails. But there's many drawbacks if we want to drill really deep. Like big improvements for this technology are unlikely. The drilling is slow in hard formations, and the cost and drill rate both decrease exponentially with drilling depth. One of the alternative technologies is millimeter wave drilling. Let's start from the basic physical principle. Millimeter waves are part of electromagnetic spectrum with frequencies, let's say, from 30 to 300 gigahertz. It has been experimentally shown that these waves are well absorbed in rocks, both granite and basalt, causing their strong heating up to the melting point and even evaporation. At the same time, unlike laser radiation, millimeter waves are weakly sensitive to the presence of dust in the air and can propagate with weak attenuation over long distances. Additionally, taking into account the well-developed technological basis, here we need to say thank you for researchers working on the thermonuclear fusion, because the most powerful millimeter wave sources are developed and used now for heating thermonuclear plasma. So how are we going to apply millimeter waves to directed energy drilling? The general schematic looks simple, also there are many technical problems hidden behind it. One of the key components is the gyrotron. This is the source of high power millimeter waves. And at the simplest level, a millimeter wave deep drilling system requires only one component in the wellbore, the waveguide, which has only vertical motion of advancement into the hole as it is deepened. The gyrotron energy output and compressed gas are injected at the surface. The rock is melted, fractured, and vaporized by millimeter waves, and the dust and solid particles are supposed to be carried to the surface by the purge gas flow. The reaming of the borehole to a diameter larger than the central waveguide is facilitated by the natural divergence of the beam launched from the waveguide. The photos on the left side show you how the process can look like in the lab for small rock samples and low gyrotron power, about 10 kilowatts. Of course, there are many other technologies alternative to conventional mechanical drilling. Some of them are shown in this slide, explaining why are we concentrated mainly on the millimeter wave drilling. Naturally, the main reason is that with millimeter waves, we hope to overcome some of the limitations of the other technologies. But let me not go deeply in these alternative technologies, since I have only 10 minutes to finish this talk. I would like only to emphasize that the main advantage that's supposed to be for millimeter wave drilling are drill rate, the high drill rate that is supposed to be constant with depth, and drilling cost that should increase linearly with depth, not exponentially. So the advantages of millimeter wave drilling have led to significant investments in the development of this technology over the past 6 years. The key player here is Quaise Energy, founded in 2018. Its activities are based on the research of Professor Paul Woskov from Massachusetts Institute of Technologies from the USA. According to the open data, funding for the development of millimeter wave drilling in Quaise Energy currently amounts to about $107 million. And for example, among the investors in 2024 is such a well-known company as Mitsubishi. Currently, Quaise is building a complex for field demonstrations. The first stage is expected to be a hybrid drilling rig combining both conventional and millimeter wave drilling. And it is expected that this will be done in 2025, this year. Here you can see some of their facilities, how they look inside, like gyrotron, transmission lines, sample chamber for testing the rock samples in the lab. I encourage you to visit and explore their website. If earlier in laboratory experiments drilling was demonstrated on small rock samples, then one of the last achievements, which was reported in 2024, is drilling a 2.5 meter deep hole in basalt. Now let's move on to our first demonstration project in Directed Energy Research Center. The main goal of this project is to design the prototype to implement state-of-the-art knowledge in millimeter wave drilling technology to drill hard rocks. We plan to use gyrotron sources with power levels up to hundreds of kilowatts for this. But at the first step that we are near to finish in the coming month, in the April, we will use 10 kilowatts, 28 gigahertz source, commercial magnetron especially. So this slide shows you what we are doing right now. We already have a gyrotron source on the left. It's not very high power, only 10 kilowatts, but it's enough to melt rocks in the lab. And it's supposed to be placed in customized container in order to be mobile, which is needed for test in the field. And the works are almost done for the chilling system for gyrotron that can support operation in the desert in UAE conditions. And for the very first tests, we designed test chamber to study all needed millimeter wave drilling processes and technologies in the lab conditions. Now we are finishing the design of millimeter wave transmission line for our system. Some parts are ready now, as you can see in this slide. Some of them are in process of manufacturing, but we expect to do the first shot this April. Let me remind that the main goal of this project is to gain experience and clarify design parameters and tasks for the next stage if we decide to go to it for the full-scale drilling. Of course, achieving this goal implies completing related scientific tasks, developing transmission lines, effective transmission lines for beam, effective mode converters, polarizers, and so on, and the determination of rock properties under intensive radiation, beam, and after irradiation. So, of course, today we are only in the very beginning of our project. This is not something that we finished or not something that we can propose some commercial product. In the coming 2 or 3 months, we are commissioning the first millimeter wave source here in UAE, and now we are actively working on the design and manufacturing of transmission line components. The first tests are coming. We are excited to start this project together with maybe to compete with Grace and other key players. That's, to be short, that's all from my side. I'm open for questions now.
Thank you very much, Evgeny, for your presentation and introduction to the technology. So any question for Evgeny? I have a question for you. Can you elaborate a bit more about the next steps about the project and also about the main limitation you have today in your development?
So the project, we expect we have like 2 stages. The first stage of the project is just the demonstration, because it's something new. It's something that is developing now in the world. The deepest hole drilled with this technology is 2.5 meter deep only. So we are only starting. And for our organizations, the first stage of the project is to confirm that we can drill at least something small in the lab, some small sample. If we decide that it's worth to work on it, we will go further to do some experiments in the field. That's why we are designing the whole system to be mobile. We are starting in the lab to test small samples. If everything will be good, we can reproduce the results of Professor Voskov, the results of Quace. We will start probably the more big project, the stage 2, the pilot, to maybe even to combine conventional drilling and millimeter wave drilling. So that's it.
Okay.
Okay, it's not the main project that we are doing here.
Yeah.
But it's something for maybe for the future.
Yeah, of course, of course. And I was also wondering, is there any environmental impact compared to other technology used for such application? Do you have any?
For the environment, you mean?
Yeah, yeah.
So I don't think that it is well studied now, but the whole rock that will be melted and vaporized inside is supposed to go to the surface together with purge gas, and then it should be filtered in some way. Because some parts, especially at high depth, can be radioactive.
Mm.
But that's only the thing that maybe can be dangerous. Of course, we need to filter it to check, but it can be monitored online during drilling.
Yeah. Yeah.
The rest is so. For example, the quays. The main goal for this technology is to go deep to build heat exchangers at high depths to maybe. This technology can it comes from nuclear fusion, of course, because it uses gyrotrons, but it can compete even with these fusion reactors, because if we build geothermal energy sources, these enhanced sources that they can deliver energy, they can compete with thermonuclear reactors, for example.
Yeah. Can imagine. Yes, please, Robert. We have a question.
I have two questions. Indeed, what's the speed comparison in drilling? Maybe you said it, but I missed it somehow. How much faster, or are you faster than just drilling mechanically? And the other thing is, do you get any feedback during the process what you are vaporizing? So do you have a chance to say, okay, this material is harder, and then you say it must be this and this stone type, or even if you are, for instance, you drill, for instance, and you just drill through the gold mine, but you cannot detect it just because everything is vaporized. How to detect that?
So the first question is about the speed. Of course, it's only expectation based on the calculations, mainly from Paul Woskov. It is expected to be like about tens of meters per hour at least. And it is expected to be constant with depth. Of course, it depends. It depends strongly on the power of the gyrotron and on the diameter of the hole. For typical diameter of like 8 inches, it can be about 19 meters per hour or something like this. But it is something that it's not experimentally confirmed. It's only prediction, expectation. The same is for the cost. It's expectation, but the technology is not well developed. What about vaporizing? Usually both granite and basalt have the temperature of vaporizing about 3,000 degrees. With little variations, of course, depending on the exact composition. So what we are, if I understood correctly, your question, what the material are we drilling? We can monitor it online, for example, by some spectrometry at the surface. when the material goes at the surface with pure gas flow, we can do some spectrometry to check what is the composition of these particles.
Okay, so you get the vapor to the surface or to the end of the
It's not
machine,
like-
and then you could try to.
Yes, it's not exactly the vapor because it will be condensed. It will be hot on the high depths, but
Sure.
on the way to the on the way to the surface, it will be condensed, but it will be small particulates that we can analyze. You can filter or do some spectrometric analysis and check.
Okay, so thank you, Robert, for your question, and thank you again, Evgeny, for your
Thanks,
nice
Tom.
presentation of the project.
Thank you.
Thank you. So now welcome our last speaker of the day, Vincent Ménoré from Exile. You are R&D quantum sensor engineer, and you will talk about quantum sensor for geophysics. So Vincent, you can share your screen and start your presentation. Thank you.
Yes. Okay. Is the screen shared correctly?
Yep. Yes.
Okay, thanks. So yes, I'm Vincent Ménoré. I'm from Exile Quantum Systems, which is a company in France. And today I will introduce what we do in the field of quantum sensors, specifically applied to geophysics. So as I said, we are a company in France. We were originally created as a small company more than 10 years ago called Mucans, and we were acquired by Exale a couple of years ago. So Exale is quite a big group. It's over 2,000 people. And in the quantum systems division, we are something like 45 people. We're specialized in quantum systems for high precision measurement and metrology. We now have systems that are in operation all around the world, several kinds of products, and today I will specifically talk about gravity sensors that we build. Something that's maybe worth mentioning is that Exale is very vertically integrated as a company. So in my division, we build these quantum sensing instruments for geophysics, but more or less everything in there can be manufactured by Exale. In particular, all the optics and photonics that go in there. So we make our own doped fibers, we make our own laser sources, which we can in turn integrate into modules and then into bigger subsystems and into the final system. And with this vertical integration, we understand and control everything that goes into our products, which makes the whole approach very coherent, and we can make sure that we understand everything in our systems. And this is quite important because building a quantum system that can go on the field is quite a challenge. I kind of like this picture. The picture on the left is what a quantum gravity sensor would look like when we started. And this is what our systems look like now. So as you can see, we've done a bit of work on the engineering side of things. And so this is what the gravity sensor that we manufacture looks like. It's made of two parts. The cylinder on the right here hosts a vacuum chamber where we trap atoms in a vacuum chamber using lasers. And we have basically this cloud of atoms that we can drop, and we measure its acceleration as it falls. And that's the value of gravity we can get. So it's all completely integrated. So as I said, we design everything in there in-house, the electronics, the software, the vacuum. We've put a lot of efforts into making the device very robust, very easy to set up. It's only a few cables that you have to plug in between the two units. So maybe I should mention that the units on the left here is where we have all the lasers, all the electronics, all the control system, and the power supplies. We've also worked a lot on making the instrument easy to operate. It's not intended to be used by quantum physicists, but by geophysicists who don't know anything about quantum physics, about optics, lasers, and so on. So everything in there is pretty much automated. The software is very intuitive. The device can be operated remotely through an internet connection, so we can make sure it's running correctly from a long distance. We can help the end users with the data that they're getting. So this came at the cost of a lot of engineering, but we had to do all that without cutting on the performance. And the performance that this kind of device can achieve is measuring gravity with 9-digit precision. I don't know if people in the audience are familiar with the figures involved in gravity measurements, but basically the daily changes in gravity due to tides, so just because the moon is pulling on us, is roughly 10 to the minus 7. So it means that we can resolve that with a very high precision. Just another figure which I like is the vertical gradient when we're moving away from the Earth. 10 to the minus 9 corresponds to roughly 3 millimeters. So with this device, we can sense a change of gravity corresponding to a difference of elevation of 3 millimeters. And with that, basically, we can install it somewhere and have an information on what's going on below the surface. So if, for example, there is some water accumulating below the surface, the gravity on the surface will change and we can measure that. Another application is volcano monitoring. We took part in a European project called Newton G, and almost 5 years ago now, we installed an instrument in an observatory here near the top of Mount Etna volcano in Sicily. The conditions are quite hard. As you can see, in the winter, we get some snow, so it's not possible to access the instrument. There's a lot of acid gases coming out of the volcano and so on. So it's quite hard conditions to be doing precision measurements and quantum physics. But the instrument has actually proven that it could operate reliably in those conditions. And it's now beyond the proof of concept, and it's integrated into the volcano's monitoring system. And if you're interested at what the geophysicists do with the data, you can look at these papers where basically gravity is used to get an information on how much mass is accumulating below the crater and how much mass is being exhaled during the eruptions, and trying to understand what's going on. So it comes as a complement to GPS and monitoring gas outlets and so on. So despite being a quantum system based on a quite new technology, it's been working very reliably and in extremely robust manner over the past years. This was just an example. We've actually built and delivered, I think now it's something like 16 or 17 of these units. They're in operation pretty much everywhere around the world. Some of them in nice observatories, like here in Germany on the top right, but some of them have been on field missions. So this is a French campaign in the French Caribbean. This is Mount Etna. The bottom left picture is measurements in Germany. We've had the device go to Antarctica for a field measurement. And so what I want to highlight here is that despite quantum technologies being a pretty young field of technology, we're managing to get a very reliable and mature instruments out of there. And of course, this is ongoing work. And I have just one slide to give you an idea of where we're heading now. This is very recent results we've obtained with a new type of instrument, which we call a differential quantum gravimeter, which basically can measure both gravity and its vertical gradient. So we drop 2 clouds of atoms at the same time. Basically, it's like having a 2-pixel camera. And by doing that, we can get very good resolution because we reject a lot of common mode effects between the 2 clouds. And some of my colleagues went to Lisbon in Portugal a few months ago. And I don't know if you know, but Lisbon is a city where there's a lot of archaeological remnants pretty much everywhere. And they conducted a survey here in the city center in what we can call challenging conditions. The day the picture was taken, the weather was nice, but they actually had some rain, quite a lot of wind, people passing by. There's a tramway line nearby. But despite that, they were able to map out the area enclosed by barriers here. and getting a map of both gravity and the gradients. And from there, we're working with a company in Italy called GRED, and they could perform an inversion of the data and infer what's below the surface. And it corresponds to what we are expecting, which is an old sewage system from the 18th century. And you can see that without any assumption on the shape, they were able to render quite well both the size, the depth, and the shape of the conduct. So this is the kind of things that we can do with quantum sensors applied to geophysics. I hope that with this very short introduction, I was able to convince you and give you a taste that these sensors are now mature and operational. As I said, we've installed over 15 of these in pretty much all types of conditions we could expect. We are working on next generations. The idea is to go from static measurements to large-scale surveys. The differential quantum gravimeter I've just showed you, we're working in the frame of another project to put it on a rover to do some autonomous mapping. We want to put these devices on ships, boats, possibly drones also, which Exhale happens to make for large-scale surveys. This can be both for navigation applications, but also for geophysics, like monitoring large-scale reservoirs or detecting geophysics features. We are also involved in space missions, next-generation gravity mapping missions from space. Well, again, I think this highlights the maturity of the technology. And on the question of what people can do for us, well, we are open for collaborations with people from the geophysics and mining community. We're quite interested in new use cases, in evaluating how this kind of technology can help and can be coupled to other sensing approaches, and seeing how we can build possibly new projects and so on. And with that, I would like to thank you for your attention.
Thank you, Vincent. It was a really interesting presentation. So much potential application. So we have already 2 questions from the attendees. So one from Yoshiaki Shikata from Sumitomo Electric. Yoshiaki, do you want to ask your question by yourself?
Sure. Thank you for the presentation. And my question is, this kind of quantum systems, quantum sensing systems need cooling to maybe the liquid nitrogen temperature?
Okay, so we don't need cooling in the terms of, we don't need a cryostat in there. What we use is called cold atoms, but it's essentially because we use lasers to slow the atoms in the vacuum chamber. So it's all happening at room temperature. It's essentially because we have a very, like the atoms are very slow because we hit them with lasers. And that's how we can get a cloud of atoms, which we can drop to measure gravity. And so it's called cooling, laser cooling, but there is no cryogenics. So it makes the system much easier to operate than anything that would have cryogenics in there.
Okay, I see. Thank you.
Thank you, Yoshiaki. Another question from Andrew Lamb from DetalG. Please, Andrew.
Hi. Yeah, so you showed the photo of these massive laser benches, obviously traditionally what you'd see in optics labs. How did you shrink your tech down into such a small device?
Well, the optics and photonics is an area where we've put a lot of effort over the past 15 years or so. Essentially, it's going from free space, visible components to fibered technologies in the near infrared, which we then frequency double. And with that, you can make systems that are both very compact, very robust, that work extremely well, and which we've now made several I think possibly 100 or so. So we have a lot of return on experience on those, and we can build a lot of things with them.
So how does your solution compare to others in the same field? So like NKP Photonics, for example, also do similar types of laser systems?
I think that, well, we could enter the details, but one thing that I think we have and possibly the others don't is when I talked about this vertical integration approach that we have, because we use those laser modules in our own instruments, we have built a lot of tools to operate them at the system level, which means that all the electronics, all the software, and how to make all these things work together as a system and not just as a laser is something that I think we're quite good at.
Thank you.
Thank you, Andrew. Any other question for Vincent? We have some question from Robert, please.
The question is, how far are the detectors away when you measure the lateral gradient? And is it, or you always say you have a cloud of atoms and you have to you drop them in the gravity field. Is it a real just that a cloud which has rather a statistics of in the atoms, or you have distinctive atom traps more several next to each other that you verify or get a valid signal from your...
No. So inside the device, which I showed, it's one cloud of atoms. So we get one measurement. The cloud itself is like a millimeter in size. Okay, so we get the gravity at one position, and then for mapping, we would transport the instrument from one side to the next. So the resolution I talked about, I don't know if that's what you're referring to, means that we could move the instruments by a few millimeters or centimeters and be able to distinguish small gravity values at this level.
Okay, and if you have it like this, how often you can repeat, or in which period you can make these measurements?
Okay, so typically the repetition rate in those devices is like 1 point per second or a couple of points per second.
Okay.
But the resolution at this rate is not as good. So we need to average over a certain number of repetitions. And so in our instruments, typically to reach 10 to the minus 9 resolution, it takes something between 20 to 60 minutes, depending on the noise and the vibrations and so on.
Okay.
And so for mapping applications, it all depends on how small or how big are the features you're wanting to measure. And with the differential gravimeter, the one I showed with where we detected the sewage system in Lisbon, because it's a differential measurement, the resolution is actually better because we get rid of vibrations that are common to the two clouds. And so we can go a little bit faster. And this is why this kind of technique is quite well suited for surveys. It has a very good detection efficiency at shallow depths.
Okay, thanks. That's cool.
Thank you, Robert. And I have one question for you, Vincent. You mentioned that you are able to detect if you have some water, underground. So my question is, how deep can you go with this kind of technologies in terms of detection? And are you also able to detect other kind of materials?
Well, the thing is, we're not selective. So if you have just one instrument on the surface and you get a variation in the signal, it could be a small source at a small distance or a very large source at a very large distance. And then it all comes to adding other measurements to try and have a complementary vision. So it can be other gravimeters where you can decouple the signals from each of them and try and reconstruct the source. The differential gravimeter, where you have two clouds, is already an indication because you get gravity and gradient, and this is like a first step. And otherwise, in geophysics, it's often coupled with GPS to measure ground deformation, measure of rainfall, evaporation, and things like that, and to try and, if you're looking at a volcano, for example, you want to get rid of the effect of water. If you're looking at hydrology, you want to get rid of everything that's not water. And so this will really depend on the application, but our instrument is not sensitive to material as itself.
Okay. And you mentioned also some future projects, to integrate this kind of technology in airborne systems. So do you plan to shrink a bit more, the whole system? What is your plan in terms of product development?
So it's basically trying to find the right balance between making it small and making it reliable. We could make it, we could build a prototype that's much smaller. Would it be a reliable industrial product? I don't know. But yes, that's the direction we're taking. The fact that we're working on these space projects, for example, means that we've put a lot of effort into the technology. We've managed to improve the reliability, make our system smaller, more compact, more robust, and so on. And this will be reused in the gravimeters that we put on ships.
Okay. Okay, thank you. Thank you very much, Vincent. Really nice to hear about this project again and this product. So several people during this meeting mentioned, the space application. So just a reminder for you that we will organize a technology meeting on space in October this year in Spain, in Granada. So you will know more about this in the next few weeks. But yeah, I wanted to let you know that we are working on a topic like this. So thank you again for all your presentation. So we'd like to thank all the participants, all the speakers today. If you need to be in contact with one of our speakers or one of the participants of this meeting today, feel free to contact me or to contact one of the EPIC team member. We'll be really pleased to introduce you to each other. So thank you again to all of you. We really hope that you enjoyed this meeting, and see you next time for another online meeting or technology meeting. Thank you. Goodbye.
Thanks a lot. Bye-bye.
Thank you.
Thank you.
Thank you.
Bye.
Bye bye. Ciao, ciao.
Bye-bye.
Ciao.
Thanks a
Thank
lot.
you.
Bye.